Welcome back to the final part of the video series Getting Started Reinforced Concrete Building Design with Revit. Looking back, we already set up our physical model inside Revit, then turned it into an analytical model with the help of SOFiSTiK Analytical Model Generator, and finally prepared it with additional information relevant for structural analysis with SOFiSTiK Analysis and Design. In this session, we complete the structural workflow inside SOFiSTiK Structural Desktop. We compute load cases, build envelopes, design slabs and columns, and talk about documentation. We also demonstrate a compact BIM change cycle so that revisions in Revit flow reliably into the analytical and FE models. Every project starts with an empty central database and is populated step by step, task by task. First, we define general system information, such as the governing design code. Next, we define materials and cross-sections, followed by the geometry together with its loads. In this project, we completed these steps inside Revit. Alternatively, the same model could be created in the traditional SOFi+ environment without using the BIM platform. From here, we are going to continue in SOFiSTiK Structural Desktop and focus on combinations. We are going to calculate the individual load cases and then superpositioning them into envelopes. We will proceed with the design of the components and finally with documentation, both as plots and as textual reports. Along the way, we take a closer look at essential tasks, such as maxima for combinations and BMS for the design area elements. We focus on the graphical user interface and set aside a text-based input, which offers extensive options for advanced users. In addition to evaluating results, we also run a BIM-based change workflow. We propagate change made in the physical construction into the analytical model and then into the FE model with minimal effort. This keeps all project participants, from the designer and the BIM manager to the structural engineer, aligned and working efficiently. With this orientation in place, we dive back into the project. We return to our project, where the physical model has already been modeled, the analytical model has been generated with AMG, and the mapping, meshing, and load application tasks are completed using SOFiSTiK Analysis and Design. Next, we launch SOFiSTiK Structural Desktop using the building template. On the right-hand side, we see the viewer with the FE model and the available load cases. On the left-hand side, we see the project tree where tasks are executed from top to bottom. We can toggle element visibility by previously assigned groups or by type. For now, we will keep the default visual settings. We open system information and verify that the chosen design code is present. We review materials and cross-sections that were defined during mapping, and we confirm the SOFiSTiK action types. We open the combination rules. Maxima generates code-compliant rules automatically. For example, Rule 103 establishes the ultimate limit state. Here is defined how dead, variable, and snow actions combine. Result load cases for envelopes are reserved starting at 2100. Next, we open the task for the calculation of load cases and accept the defaults. Rerun the analysis and obtain deformations and internal forces for each load case. Viewer now contains and displays results, such as the reaction forces in the tooltip for each load case, or the deformed structure if activated with the toggle switch. We can quickly review the automatically generated report to check load sums and example plots such as principal moments and beam bending moments. Let's open superpositioning for combination rules. We run the superposition for ULS and for SLS. If we look, for example, at the nodal forces in combination 103 ULS fundamental, we see the following. Load case 2101 stores bending moment mxx max, 2102 stores bending moment mxx min, and so on. The calculation takes a little while because in each combination, the results for all the elements must be superpositioned individually. Opening the report for the task, we verified that the combination formula, partial safety factors, combination factors, and generated result load cases are all documented. Let's add a new task. We go to Post-Processing, Interactive Graphics, and rename it to Bending Moment, Foundation Slab ULS. We navigate to Results, Quad Elements, Forces, Bending Moment MXX, and switch to Result Load Case 2101. Next, we restrict the view to the Foundation Slab group by selecting Group 10 and switch to a top view. On the third tab, we can choose from a multitude of display styles for the results, such as filled areas or isolines. Under Edit Cuts, we can draw evaluation sections under the columns. We switch the display style to cut line results and adjust the text size for readability. For instance, we can see values of around 110 kilonewton meters per meter under the interior column with the tension on the bottom face. We save the view and exit. Moving on to the design for the slabs. We open design parameters of area elements. We add a row for the foundation slab, which is group 10, and choose two orthogonal reinforcement layers. We keep the reinforcement aligned to the local X and Y axis. We define the concrete cover at axis distances. With a nominal cover of 25 mm and a 10 mm diameter in the first layer, we set it to 30 mm to the first bar axis. Between first and second layer, we use half diameters. So for an assumption of diameter 10 and diameter 6, we set it to 8 mm. Additionally, we set the bar diameters to the aforementioned 10 mm for main reinforcement and 6 mm for secondary reinforcement on both faces. For the crack width, we choose a limit of 0.2 mm for main and secondary reinforcement. Let's have a look at Design ULS area elements. By default, we store results in Design Case 1 and keep code-provided partial safety factors. We ensure that the ULS envelopes, including load case 2101 for MXX max, are active. For shear, we leave the compression strut angle to be determined automatically by the code rules. For punching, we allow an increase of bending reinforcement up to 1.5% of the concrete area before shear reinforcement is added. We run calculation and confirm that no warnings or errors are reported. Let's add another graphics task and give it a proper name. Upon opening it, we see that all the design results are available. On the fourth tab, we can manage the individual plots. A graphic is like a sheet of paper in the report, where multiple pictures can be arranged. Additionally, it is possible to have multiple layers with different results on top of one another. But first, we filter the view to group number 10 again and go into top view perspective. Now let's focus on the lower reinforcement in first direction and then add a layer through the respective icon and select structure, and again for punching. Let's adjust the decimal points and text sizes for readability. We also want to use the element values and not the null ones. There are many optional settings to influence the display of the results, but we will ignore them for now. Zooming into the area with the 4 interior columns, we see the punching cones around each column. We observe a uniform flexural demand of about 11 square centimeters per meter. Outside the cone, the required reinforcement drops sharply. This pattern indicates that the punching check was satisfied by increasing bending reinforcement without adding shear reinforcement. We duplicate the graphic and switch the reinforcement layer to review the other direction efficiently. We save the views and leave graphics. We open Design SLS area elements. We base the calculation on Design Case 1, ULS, and store results in Design Case 2, SLS. We use the quasi-permanent envelope and select the direct crack width calculation. We execute the task, then duplicate, rename, and open the graphics task. Here we can delete the layers with the punching results and focus on the required reinforcement. When switching between the design cases, we can see slight variations. For a better overview, we can activate the decisive design checks and change the style to filled area. We can now see clearly where punching becomes decisive, this is the yellow area, and where crack width based on calculation is decisive in red. We return to the other design result, exit graphics, and are done with the slab design. Once we calculate the task, we can see the static result plots from the time of calculation inside the report. Next, we are going to focus on the columns. Let's start by adding a new task group and giving it a descriptive name. Let's add the column design assistant. The assistant groups columns automatically by section and length, for example, diameter 25 centimeters round, or rectangular sections 100 by 25 centimeters. The naming is inherited from Revit, which supports traceability. We can keep the default options such as eccentricities and support conditions. On the tab Combinations, the assistant lists load case combinations per column, which can differ from the envelopes created by Maxima. We run the calculation and review the report to identify the decisive combinations, for example, combination 1002. This includes a combination of 1.35 times G, 1.5 times snow, and 1.05 times live loads. In many cases, the utilization is governed by minimum longitudinal reinforcement. For rectangular columns, this means 4 diameter 12 bars, which corresponds to 4.52 centimeters square. The summary table highlights the governing members in each group. For large projects with many columns, this is a very helpful overview and would also allow us to regroup and change the reinforcement layout for highly utilized columns. Next, let's test run a BIM change cycle with AMG. We're going to assume a planning partner, for example the architect, made some design changes and decided to exchange a column. The in-house BIM modeler already copied these changes in the shared BIM model. But how do we continue from here? We return to Revit and open Analytical Model Generator again. Once we run the check step, we are informed about these changes in the physical model. The report after the step lists differences between the physical model and the analytical model. To update our analytical model, we log all analytical elements except the analytical members we would like to change. When we return to the generate step, only unlocked elements are updated. Afterwards, when we run check again, we see that the step finishes successfully without any warnings. We continue by switching back to SOFiSTiK analysis and design, compute the main system, and then return to SSD. Here we can note the updated sections, specifically the new section 6 with a diameter of 20 centimeters has been added. Legacy sections remain in the CDB but are no longer used. Now we run the slab design up to SLS once more and inspect the affected slab group in graphics. We typically observe reasonable reinforcement patterns with localized high punching utilization near the revised supports, while the underside is not ruled by punching. We rerun the column assistant and note that round columns, such as the diameter 20, are often covered by minimum reinforcement according to Eurocode. In our example, this is a little higher than before. Before we end this tutorial, let's have a look at one more way to display and communicate results directly inside Revit. For that, we return to Revit and use the Show Results command on the SOFiSTiK Analysis tab. A side panel called Result View opens and allows us to choose from a wide range of results. For example, we can look at column results, specifically normal forces, and select any of the single load cases, but also all the envelopes. Or we select the display pattern reinforcement slab's bottom layer to look at the results we investigated inside SSD. These results are taken live from the corresponding SOFiSTiK CDB. With the command Save as Package, accessible through the ribbon or the side panel, it is also possible to save them in so-called result packages inside the Revit file, which allows us to share them with other Revit users. But that, as well as many other features such as beam design or deflection, is a story for another day. This tutorial aimed at showcasing the most important tools, from setting up a physical model to efficiently turning it into an analytical model, then enrich it with the necessary information for structural analysis and design. Thank you for watching and have fun working with Revit and specifically SOFiSTiK.